Thank you. Okay, so hi everybody. So I'm Gabriele Paoloni. I work for Intel as a senior software architect for functional safety, and I'm also leading the safety architecture working group in ELISA. And this is what we are presenting today. It is the result of a joint collaboration between myself, Daniel, and also the rest of the safety architecture working group people. Okay. Daniel, I don't know, you want to quickly introduce yourself?
Yeah. So hi, I'm Daniel. I'm a kernel engineer at Red Hat. And that's enough.
Okay, good. Okay, quick disclaimer. So this is work in progress, and indeed, so here we are not making any claim with respect to this work. So it is an exploration, okay, and so this is an exploration that we are doing, and we don't want to make any safety claim, okay, that based on this preliminary report, okay. Agenda. So today we'll first touch on what is in scope and out of scope for this presentation. Then we talk quickly about possible functional safety qualification approaches for Linux. Then we'll introduce the hybrid qualification approach that is the main topic for today. We'll show an example. And then we talk about the integration testing through Runtime Verification Monitor. And then we'll touch about next steps, and we'll take question and answers. In scope, indeed, so today we want to talk about a proposal and a high-level description of a functional safety qualification flow for the kernel code allocated with safety requirement to meet a certain ASIL. We will not talk about the functional safety qualification of the hardware that we assume to be already qualified. And we will not talk about functional safety qualification according to standards beyond the ISO26262. And we will not talk about freedom from interference claim between coexisting kernel partitions allocated with different ASIL levels. Okay. I will go quickly through this because I think we had enough about this in the previous session from Roberto. As you know, there are mainly three practical options to qualify pre-existing software component. One is using part 8.12. That is a black box approach, but it is commonly accepted only for simple software components, okay? Whose behavior can be comprehensively described by the top-level specification. We have part 6, so we can assess and re-engineer a pre-existing software component according to part 6. This is a modular and hierarchical white box approach. And indeed, it is suitable to develop and assess software components of any complexity. We have the part 8.14, that is a qualification approach based on proven in use, so that if you have enough statistical data about failoring times of the software component that you are considering, you can leverage this statistical data, assuming that your context of use is the same as the one where the statistical data has been collected, okay? Indeed, this approach is harder to scale to different hardware configurations and also use cases, okay? Because the deployment condition must be replicated, okay? And then we have part 10.9 that is not a practical option at the end. So part 10.9, it just explains the concept of safety element out of context. And therefore, it talks about assumed safety requirement and assumed nominal requirements and condition of use that you must respect if you intend to reuse a safety element in different contexts. However, on the practical side, you need to follow other methodology for the qualification itself. So it doesn't provide an option in reality, okay, a practical option. So the part 8.12 standard approach. So here we can see that from a life cycle point of view, we have the safety and nominal requirements specification. Then we have the pre-existing code, and then we have some requirement-based, extensive requirement-based testing. Okay. It is quite simple, and this is why it is commonly accepted only for simple software components. Okay, in this case, indeed, the amount of collaterals that must be maintained is low to medium. Okay, if we go to the part 6 standard approach, we can see that there are many more phases that are standardized and that must be met. Okay, and as we go down into the life cycle, especially when we fall into the unit design, unit testing, and implementation, the amount of collateral that we need to maintain, it increases more and more and more, and actually it can explode for very complex software components such as Linux. So. Indeed, so given the current state of ISO26262, so Linux is too complex to be qualified according to part 8.12. The safety element out of context only covers the requirement definition and doesn't give us an option. Okay, we could assess and reverse engineer according to part 6. However, the application of this approach is quite challenging, especially considering the amount of work and the amount of collaterals that must be maintained. It could be qualified according to part 8.14, the proven use, but only if statistical data is available for the specific hardware configuration and usage conditions of the target system where Linux is deployed. Okay. Pain points in Linux if we want to follow the ISO part 6. Indeed, we need to specify all the requirements and specification for the different unit, so for the single function, effectively. So we need the informal notation for ASIL up to B, and we need the semi-formal or formal notation for ASIL C and beyond. Plus, on the implementation side, there are different rules that we should follow. Okay, that you can see like listed here, a subset of them. Okay, one entry exit point, no dynamic object variables, no multiple use of variable names, no implicit type conversions, no unconditional jumps. Okay, and also we need 100% of code coverage and the requirement coverage of the single software unit of the single function. Okay, so in practice, the effort to write and maintain the documentation, tests, and infrastructure is not really viable following part 6 as it is. So we have a dilemma here. So Linux is too complex for part 8.12 and part 6 is too complex for Linux. So what do we do? So what we have talked about in the last month or couple of months in the architecture working group, we try to follow a sort of hierarchical and hybrid approach. So divide and conquer. And what do we mean by divide? What do we mean by divide and conquer? Okay. So the idea would be to do a partitioning of Linux in blocks of software elements. We can define each block as a software unit, and we qualify each software unit according to part 8.12. And then what we do, we follow the ISO26262 part 6 to assess the kernel as an integration of multiple functional safety qualified units working together to meet a certain ASIL target. And on the right, I mean, I'm trying to depict what I mean. Okay, so you can see that here I've partitioned the Linux in different blocks. Okay, I mean this picture is only for presentation purposes. Okay, it's not complete, it's not correct, right? It's just to show the concept. Okay, each of the block can be qualified according to 8.12, and they are integrated together following the part 6. And this is the description from a life cycle point of view. You can see that down to the software architectural design. When I say software architectural design, I used exactly the nomenclature of the current ISO26262 part 6. Okay, so down to the software architectural design, we follow the part 6. Below that, we move to part 8.12, and the reason why we move to part 8.12 is to relax the amount of collaterals that we need to maintain. Okay. So safety validity of the hybrid approach. Indeed, I mean, from a safety point of view, the 8.12 is already used to qualifying pre-existing software components of limited complexity. And indeed, if a software component is functional safety qualified, it can be integrated into a software framework assigned with the same or lower ASIL target. Okay, this is as long as the assumed safety requirement as well as the condition of use are defined and met. Okay, and as I said before, the idea is to have in Linux the integration of multiple qualified drivers and subsystem in a hierarchical, scalable way. So what is the tricky part here? Okay, here it is important to decide what is the criteria for a single subsystem or driver, so a unit, to be simple enough to be qualified according to 8.12. Okay, how do we judge if a partition of Linux is simple enough so that 8.12 can be applied or not? And so this is the explanation of the proposal from a practical viewpoint. Okay, so the first step will be to define and allocate assumed safety requirement for a critical unit, a partition of the system. Then we have two different paths. One is the creation of a semi-formal or formal specification for the unit in interacting with other units. Okay, so this is for the software architectural design. Okay, at the same time, we need to document the specification of the critical units using the informal notation. Okay, so that in terms of kernel doc, so effectively following part 8.12, we need to define the specification of the critical unit. So on one side, we have the specification of each unit. On the other side, we have semi-formal notation or formal notation to specify the interaction between the units. This architectural and design information is used to write the safety analysis. And the safety analysis on their side are used to write the K-self-test for the qualification according to 8.12, and then we have also K-self-test for the definition of the integration test. Okay, and the idea here is to cross-check the system and the specification using the runtime verification and K-self-test results. So the runtime verification will be introduced by Daniel later on in this session. Okay, and indeed here we have two feedback paths, one from the verification and another one from the safety analysis into the requirement definition. Indeed. Okay.
Gabriel, there's a question in the chat.
Yeah, if it's okay, I would like to take the questions.
Later. That's up to you.
Yeah.
You should be aware of it.
Okay. Yeah, no, later, because I mean, it's quite a dense presentation, so I cannot take all the questions right now. Otherwise, I I'm worried that we will not come to the end. Okay. Okay. So indeed, here we have also a continuous integration here to monitor the changes on one side. On the other side, it is optional. We can use runtime verification to monitor the system at runtime. Okay, so we'll not cover about this today, I believe. Okay, so now, as we said before, how do we partition the system into software blocks or unit to be qualified according to 8.12? And what is the right granularity to make a unit simple enough? So what is the criteria that provides the confidence on the right granularity? So as of today, 8.12 requires the specification of the software component to specify known safety requirements, functional requirements, behavior in case of failure, resource usage, description of required and provided interfaces and shared resources, and also configuration description. Okay, so if you're able to specify comprehensively in natural language all of the specs above, the level of the granularity for the single unit is the right one. So the idea, the principle here is that when we write the kernel doc header to specify the associated to the entry point of a kernel block or unit, okay, they must be comprehensive enough so that the behavior of this single unit is clearly specified. If we are not able to do that, it is not the right granularity. So we need to split further, okay? Okay, so this is how to partition Linux, okay? We know that as of today, Linux is already partitioned, and maintainers, that is a file in the Linux tree, can be used as a starting point, okay? Probably it's not the right one, okay? But at least we have a starting point, okay? And indeed, maintainers is also good because we can map the code also to the people that are responsible for it, okay? And indeed, if a subsystem or driver is too complex, we can subdivide it further, okay? So right now, we are using maintainers as a starting point. It is the right one? Probably not. Probably it will be split further, but yeah, we are starting from there, okay? And here I'm trying to explain with an example, okay? So if you look what we did in the architecture working group, so we started from the telltale use case. Okay, so this is a picture of the safety concept, and so I can skip this because it was already touched in a different session. From the technical safety concept, we have defined safety requirements. An example of kernel safety requirement is that the watchdog subsystem shall ensure the watchdog timeout to be set according to the ioctl input parameter. Okay, so this was the kernel safety requirement that derived from the safety concept. So in the architecture working group, we focused on the ioctl in the virtual file system, okay? And so we said, okay, let's start with the maintainer granularity, okay? So the ioctl is defined, okay, so first of all, a software unit block is defined as a group of C and H files, okay? So C file and header file. If we look at the ioctl, it is implemented and maintained in the VFS, and the scope of the VFS is clearly defined in the maintainer file, okay? So everything that fall into the F scope here of this file, so FS include Linux fs.h, all of these files are in the scope, okay? The X means you need to take these files out of the scope, okay? So it's pretty the principle is pretty simple. Okay. Now, working at the granularity of the at this granularity of VFS, what we did, we built a communication diagram. Okay, so you can see that the file system, VFS, and infrastructure is the target subsystem driver that we want to model. Okay, and then we have the pink subsystems are those that our target one it communicates with, and then there are some subsystems that are marked with dashed line. These are generic one. Okay, so for example, we know that a yoctl will on the output side will call a function pointer, unlock the yoctl that can be assigned to different callbacks depending on the driver that it talks to. So in this example, we took the watchdog device driver, but can also be other. Okay, and as well as the Arch subsystem. For example, we have different possible architectures that we are running on. In our example, we used x86, but they may be different one. Okay, and you can see that. So with respect to the communication diagram, what is important is to define the incoming function with respect to the target file system, to the target subsystem, and the outgoing functions. Okay, and here I'm just highlighting two examples. Okay, so the incoming function is the ioctl syscall from the user space, and one of the outgoing function is the ioctl callback. Okay, so the unlocked ioctl callback. And here I'm also presenting, a snapshot of the sequence diagram that show how the target subsystem is communicating with the other subsystems that were presented in the communication diagram. Okay, so this is not complete, otherwise it would not fit the presentation. You can see, at the link, you can have like the whole architecture. Anyway, you can see that at the level of the software architectural design, we have used the semi-formal notation. Okay, so we have depicted, we have reverse engineered the component, and we are showing how this component communicate with the other components of Linux. Okay, so this is the important information here. As we move down, we say that our input API is the ioctl here with respect to this component. So what we need to do in order to qualify the VFS in the context of the ioctl, we need to specify the behavior of VFS when ioctl is invoked. Okay, and this is what we put together. Okay, so this is a brief. I mean, right now we don't have any description we don't have any kernel doc header for ioctl, if I remember correctly. Okay, so and this is what we could propose, for example. Okay, and the idea here is, to be able to specify the expected behavior well enough so that the kernel self-test can be written and can be evaluated against this specification. Okay, and also a safety analysis was performed, mixing together the software architectural design and the block specification. Okay, so that we can following this safety analysis, we can refine on one side the safety requirement, on the other side we can also we can define what are the aspects that we need to focus on during the test campaign. Okay, and then indeed, okay, so this is the pre-existing code of the ioctl, so there is nothing, not much to say about this. And as we go up on the other side of the V diagram, so this is all to be done. Okay, so but the idea will be, as I said, to define test specification for the 8.12 qualification of the single block. And on the integration test side, we can use Runtime Verification Monitor to verify the single block to behave as expected in communicating with the other blocks. Okay, and using this Runtime Verification Monitor, if either the code is wrong or the model is wrong, an exception is raised and the test fails. Okay, and now I will leave the scene to Daniel to introduce to talk more about this Runtime Verification Monitor.
Yeah. So keep controlling these slides, please. Yes. So I've been talking about runtime verification on the Linux kernel community for quite a while. So, but just recalling things, runtime verification is a lightweight but yet rigorous form of verification method. And it works basically by, instead of analyzing a re-implementation of a system in a model, on a model language, it interprets the real system by observing the trace of the events that system generates. And it's more suitable for complex systems where we cannot re-implement a model of the system, but just implement a set of specifications, right, on how the system should behave, and then monitor the system by observing the events. Next slide. So where is the runtime verification on our approach? It actually closes the loop between the specifications that we write and the actual design of the system, right? So it loops the kernel and the documentation, and it allows us to, let's say, like just on a very soft way, it allows us to run part of the documentation inside the kernel. And that's useful for two things: for the continuous integration of the tests in the kernel, and to perform runtime monitoring of the system as it runs. Next slide. So just one idea, overview of how runtime verification works. The central part of the runtime verification is a runtime monitor. In one hand, it receives the kernel tracing, and the other hand, it receives a formal or semi-formal specification of the things that we want to analyze or verify. So the monitor receives the trace and tries to run the specification. If everything is okay, the monitor doesn't complain, but if an unexpected event happens, it can cause some reaction. For example, it can fail safe the system to a safer state, or it can warn and point to the problem, and then we can go there and try to rework the specification. Next slide. So first question, I saw a question about if there are cases of application of formal methods to the open source projects, and yes, there are a lot. I'm just showing here one of these many examples that I did myself, which is the thread synchronization model for the PREMPT-RT. And I used Automata for this kind of verification. And by using a modular approach, I could model, by using small pieces, the thread synchronization model for the PREMPT-RT. That is a very huge model. And this always published on very well recognized journals in the academic world. And we are starting moving these into practice into the kernel. Next slide. And the next questions about the application of formal methods in the kernel is usually how efficient can this approach be, right? And in the sequence of that work where I built a model using Automata, I also did an efficiency analysis of that approach. And in a long story short, it shows that if we do the method that I will talk later, that I created to verify the kernel as it runs, verifying each event from the kernel is faster than just tracing it and saving it to the trace buffer for later analysis. Again, this is a long topic, and I suggest you person interested on it to search for the title of this paper. It explains the methodology. Next slide. So Gabriel's idea was to create a sequence diagram to semi-formally explain the behavior or the interaction among the subsystems on the kernel based on their interfaces. And the good thing is that this sort of diagram can be easily converted into the automata that I use on my verification technique. And it's very straightforward. Next slide. And okay, and the final question is how hard is to apply, to transform this documentation into something that we can run inside a kernel. And 1 hour before this talk, I've submitted the first version of the runtime verification interface for the Linux kernel, right? Which is the sequence of the development of that theory that I presented on papers. So it basically presents 2 things. It presents a tool that takes an automata and transforms it into a monitor code. And it also presents an interface based on ftrace. Next slide. So for example, this is WAP file is an automata represented on a graphics format. It's an open format. And by just running that command line, the tool.uk transforms the code into the 92% of the monitor code, right? It also uses a set of macros that resembles the trace event infrastructure on the kernel, which is part of the tracing subsystem. And as I'm relying on trace subsystem, I'm using the same abstractions that Steven puts there. So the work left to be done for a developer is to connect the events that he uses on the model to the events that kernel emits. And there is a link here where I show an example of transforming a model into a monitor and how to link the monitor to the kernel. And it's pretty straightforward. And the good thing is that by reusing the kernel interface for tracing, I can use anything that I can hook a function, like using a trace point, hook to another function or a kprobe. And on the RFC, I give examples of how to do this kind of transformation and instrumentation. Next slide. And also, so the interface for runtime verification is pretty easy. So for example, here, I'm showing that to enable, starting back. So the interface is based on ftrace, and for kernel developers, it's very straightforward, right? So here's one example on how to go to the interface in the first line of the shell here. In the second line, I restricted the monitor to react to an exception, and the reaction is to panic the system. And in the third line, I'm enabling the monitoring. So it's very easy to deal with these, also the monitoring in kernel. And the developer can watch the monitoring of a formal specification using the ftrace interface as the example below. Next slide. So this is a very huge topic, and it's the results of years of research and exchange with the kernel community, many with people in tracing. But just for you to get started, there are a lot of documentation on the subject. In the last 3 Red Hat Research Quarterly magazine, I present a summary of this research. And you can find here the 2 papers, the academic papers that I presented, the background behind this formalism. It's a little bit heavier to understand this kind of documentation, but it's a good sign. So this was reviewed by the academic community. And the formal academic community is a very strong community. So this is a very good evidence that the approach is on the right direction. And there's also a talk that I gave at the LC 2019 where I present these ideas in a more, I'd say, for kernel developers way. And I think that's my last slide.
Okay. So, okay, thanks, Daniel. So, and so now we talked about.
Thank you, Gabriel. Oh, you were going back, or you have time for questions, or you're.
Let me just quickly finish, and then I think we are almost done anyway. So, and okay, so we talked about integration tests using Runtime Verification Monitor. Indeed, I mean, top-level platform and validation tests can be carried out according to the allocated kernel safety requirement and safety requirements from the telltale safety concept. Okay, so if we talk about the telltale safety concept. So next steps on our side is, so we need to complete the evaluation of this hybrid approach in the context of the telltale use case for the automotive, from the automotive working group. We need to refine, finalize, and build consensus on the hybrid approach in the development process working group. We talked a lot about software architectural design diagrams, okay? We need to develop and refine tools that can augment and support the generation of these software architectural models, starting from the code, okay? And indeed, we need to continue the development of the runtime verification interface. And finally, we need to go, if all of this prove feasible, it is accepted, we got a consensus, then we need to go high scale, right? So we need to start pushing the tools and engaging with the maintainers, okay? So, but this is indeed the very last step, okay? So now it's time for questions. Okay, where do I need to start from? The top, I guess.
Yeah, and Daniel has been very helpful all along. He's answered some of the questions. So
Okay.
Daniel, you can pipe in if the questions have been answered already and save some time. Okay, thank you.
I don't know, so let's see.
I've been trying to reply some of the questions, but I think that there should be more. So I think that if anyone would make a question that is not replied yet, it's free to make questions.
No, definitely, but just Daniel will save Gabriel repeating in case you did already answer. That's what.
Okay.
Great.
Okay. All right. So can you give an example of pre-existing software already qualified with ISO26262 part 8.12? I mean, open source software. I mean, from my personal experience, I know of some libraries that have been qualified using part 8.12. Okay, and but open source software, I don't think there is any that I'm aware of, to be honest. However, 8.12 is indeed like an approach that is quite used for simple software component. Usually, it is used for libraries, that are simpler compared to operating system. Okay, so I'm not aware of operating system, for example, that are qualified according to 8.12 alone. Okay. So we have sure what does assumed in the context of safety requirement. Assumed, it means that you are not you're making an assumption on your requirement, okay, and because you assume that it is important. This is what is important from a safety point of view, okay. So I don't know, for example, if you have the Yoctol, let's make an example, okay. So from a watchdog, from the telltale perspective, we use the Yoctol to set the timeout of the watchdog, okay. An assumed safety requirement for the Yoctol would be that the right callback is invoked according to the input file descriptor, okay. So this is an assumed safety requirement that would fulfill partially, at least, the safety requirement specifically in the context of the watchdog, or in the context of the telltale, okay. But it can be reused also in different contexts, okay. So it is a way, to make assumptions on your requirement so that your software objects can be ported to different context of use. Okay.
Just Gabriel, if anybody, this is to the audience, has something to add, instead of writing at this point in the chat, you can just pipe in and comment or add something to what Gabriel said. Inviting the audience to be a little more active. Okay, thank you.
Yeah. Okay, so the next one is, please excuse my ignorance. What is part 8.12? I'm aware of part 6. Yeah.
Gabriel, Sriram here. I got the answer already, so you can skip to
Oh, okay, okay, good. Thanks. Are there examples of semi-formal or formal specification for any open source software? I think Daniel gave the example, and the Automata is a formal one, right?
Yes, it's a formal one.
Yeah. Be good if you can indicate how many additional tools there are here and how you are going to argue these are not TCL3. Well, this is quite far. Okay, so this is so right now we are first trying to, to evaluate the applicability of this approach to Linux. Okay, so indeed, all the tools we are working with, we are not qualified them. It is a gradual approach. Okay, so first we evaluate this qualification approach to be the right one and to be feasible. And if we say, okay, it is feasible, then as a next step, we can think about how to qualify the tools that support this approach. I mean, I mean, qualifying the tools right now, I think it's too early, to be honest. Shua, how do you define reverse engineering in this context? Reverse engineering means that we need, so we start from the code in Linux, okay? So if we are, for building the Automata model or the UML model, indeed, we need to manually look at the code and build a model according to the code, okay? We can use tools to speed up the process, but from a safety point of view, the model must be reverse engineered by human, okay? So, and this is what I mean. Also, when writing the kernel doc header, the kernel doc headers, they must be written following an understanding of the code, okay, that we read.
So reverse engineering means different to different people. Probably you might have to put that in context.
Okay.
So that's, I understand what you're saying. You're actually talking about taking looking at documentation, looking at the system calls or IACTLs or a particular module is using, and developing a footprint for that module. Reverse engineering, for example, means that take that as a block, anything as a black box, and feed inputs and get outputs. And then based on that, figure out what are the internals of that. But that's not the case here, right? We have the code available. We have everything available. You're not really guessing anything by feeding input. So in that context, I think that reverse engineering is not the right word to use in this context.
Okay, yes, that's a good feedback. So I will, okay, so I will take this into account and I will try to find a better nomenclature, or at least I will add a note explaining what I mean by reverse engineering. Yeah.
Thank you.
Yeah, thanks.
Just to comment on, I would say in a certain field you are doing reverse engineering of the model, right? No, it's the other way. Yet the black box is your model. You don't know the model, you don't know the design, you don't know the architecture, and you have the code. Your code is your things you feed in. So maybe for your consideration, this is more the reverse engineering of it, because you reverse engineer architecture. Your architecture is the black box. isn't it?
Yeah, if you look at the code as a black box, yes. I mean, I'm trying to decode this black box and create a model. Okay, a model and the specification of the input API of this block. Okay, and yeah, but effectively, I don't like. I mean, it's not a black box because, as Shua is saying, that the code is there, right? And the way we do it is we reverse engineer by looking at the code, effectively, with the help of tools. But indeed, I mean, it is important to have the human action. Okay.
So Paul just called it reverse specification, which may be a better word for it.
But Philip has a point here. You're looking at the code and you're reverse engineering the intention of whoever wrote the code. Anyway.
But the question remains whether that written code was meeting the intent of safety. If not, was that discovered and the new changes were brought in the architecture?
Yep.
But we don't need, okay, but I mean, we start from the code, okay? So from the code, we can definitely derive the specification, okay? The specification, they are objective regardless of the intent. I mean, how a octal works is objective, right? Then if during the safety analysis, I find out that it doesn't meet the expectation from a safety point of view, I can propose a change to the code, right? Or do something else, I don't know. But I mean, what I'm trying to say is that the stage of reverse engineering is just is very mechanical, like it's looking at the code and explain what the code does.
So basic question, Paulo, that remains, right? The code was written for certain requirement. Maybe it was not on the paper, but was in the minds of developer, right?
Yes.
Now you are testing that code, right? You are doing a reverse engineering, you are creating a documentation, and you are going further and testing it, right? But the gap that remains still was that initial concept that developer has was good enough to support the safety. Right. So my, I mean, doubt still remains whether you were able to find certain, certain gaps in the existing code and architecture. That would be a good example to showcase.
Yeah, actually, in the next session, we'll talk about the watchdog, and I will give you a specific example of a possible gap. Okay. So, but the idea here is that once we have the architectural model and the top level specification of the block, we are able to do a safety analysis, and therefore to evaluate, the goodness of that design in meeting allocated safety requirements, right? If it is not good enough, we can propose changes, right? The problem that
Paulo.
Yeah. Okay, so Lucas, could you not, sorry, anybody? Okay, so Lucas, could you not just skip the safety analysis, just write tests? Your approach basically says write tests. No, not really. One of the reasons is what I just explained, right? So we derive, we build the model, the design model for the block and for how the block interacts with other block, and the safety analysis is needed to verify on one side the goodness of the design with respect to the allocated safety requirements. On the other side, also to possibly tailor the test campaign against the more dangerous failure modes. So I think the safety analysis is quite important. Yeah. Okay, I found it in the ISO. Okay. I think this is covered. I can't understand why LKML is mapped there at the flow. Yes, because there wasn't. Because when we use maintainer, there are some files that do not map to a specific component. So, and this is one of the limitations of currently of maintainers, okay? So it is a starting point. It will, we know it will not be used as a final way to split the kernel, okay? But again, there are some files that just map to the general to the mailing list of Linux, and they don't. I mean, they don't have any specific tag in terms of a component, subsystem, driver. Okay. There are so many errors in maintenance. Yes, yes. I mean, it's a starting point, Lucas. It's we are aware. It's yeah, exactly. So yes, 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 yes. Okay. Okay. What does Linus think of this? I don't think Linus ever saw this. I mean, I think we'll go to Linus if you know, if it is suitable later on. We'll probably, before talking to Linus, we need to talk to other guys about this. Okay, so does Runtime Monitor access workload in this context?
Yeah, Daniel answered that question. Thank you.
Okay, okay.
Answer for that.
What is the performance overhead of using ftrace-based monitor? I think in case it is not acceptable, do you have any other potential backend that could be used for the same purpose? Was this answered, Daniel? So Daniel, did you answer the
An easy answer is that we can use trace on the production system to monitor the system. And the overhead of running an automata as a monitor in the kernel adds less overhead than tracing itself, than writing trace to the buffer for later analysis. So it gives us good hopes that the overhead, which exists obviously, is low enough to be considered for critical parts of the kernel.
Okay.
Then
Great,
there
thank
is another question. In case of system call, I don't know if you noticed that, if you have answered that question. That's an interesting one for me as well. There is one more question here.
Question is at gap. In case of system call, the first entry point is a software interrupt mechanism on architecture-specific components. Is this part including the octal part in your figure or architecture part?
Where should I look at?
Just before the last question you answered.
Oh, sorry. Okay, sorry. In case of syscalls, sorry, I'm first entry point is a software interrupt mechanism on architecture-specific component. Is this part including the octal part in your figure or arch part? Okay. Why? I mean, why the first entry? I mean, here we are basically we analyze the requirement of setting the watchdog timeout. Okay, that was done through the octal. So now when you say the first entry point is a software interrupt mechanism, an architecture-specific component, what do you mean?
Yeah. So in case of call IO control call, so first step we call system call wrapper inside the libc. So libc using the software interrupt change moving into the kernel space.
Oh yeah. Okay. Okay.
Yeah.
So
This means.
Yeah. No, we didn't. Okay, so the scope was here is the kernel. We didn't cover the glibc. Okay, so we started from the kernel. Okay.
Yeah.
So that's yeah. Okay. I can hardly follow this chat as you guys are continuing to type. Okay, so conclusion, a probably reverse engineered model from an implementation can be verified to fulfill the claim. The model fits to the implementation. Good job. Compliance achieved. Thanks. Sure, the runtime monitor runs hooked to the application kernel, so there is no RV process for the automata formalism. Implementation. Okay, so this was an answer to Shua. Can you say which libraries? What is the level of percentage coverage through doing requirement testing on safety relevant part? So Sanjay, here you're talking about the dynamic, I mean the code coverage, right?
Yeah.
Okay, so yeah, this is a point that we have not touched yet. So I think it's a point that is open for discussion. So, and the question will be, using the hybrid approach, do we require code coverage? So because I mean, formally speaking, if we want to follow part 8.12, the code coverage is only required for ASIL D, okay, and not for lower ASIL. However, since we are talking about an operating system, maybe that is not the right choice, okay? So this is something that we need to discuss, to be honest. The good thing is that, you know, since we are testing at the level of block, it is definitely easier, you know, to achieve a certain degree of code coverage, okay? Because, you know, like we are not testing from top level syscall, and we need to have coverage down to the nitty gritty part of Linux, right? So we need to have, you know, self test for each of the blocks, okay? So, but this is an open point of discussion, and to be honest, we haven't touched on it yet.
So, Paulo, I understand you have a concept of SR, non-SR, right? So at least
Yes.
I was thinking for the SR part, right? You want to show the sufficiency of your testing, right?
Yes, yes,
and
yes.
The coverage data is a good indicator that you have certain test cases
Yes.
which ensure that at least all the code path and then the conditions, they are met and, you know, truly evaluated in testing environment.
Yeah, I fully agree. And as I said, it's a point for discussion, and I would expect to touch on this point in the development process working group as we refine and dig more into this approach, okay? Lucas, there is a big conceptual bug in this approach, but I fear you need to execute a few times to understand the conceptual bug. When you're ready, let me know. Okay, well, it's a bit cryptic. I don't know. Yeah, we'll let you know. Nicholas and I did that a few years ago. Yeah, if you can point to the documentation, to what you did, maybe you can save us some time. Johan, I don't think that introduction of highly formal methods and open source development can go together. Please, there is lack of proof on compliance in a pure open community. Was this answered? Okay. Why? I mean, I think we'll answer this as we try to go high scale, right? I mean, we are introducing here the formal or semi-formal methods to integrate the different components, right? We know it's not there. This is a matter of fact, right? So we need to see what is the reaction from the maintainers. So we don't have an answer here yet. I get it's well developed. Keep on going, Sanjay, and so that there is no increased confidence. Okay. Man, 14 new messages. Johan, we need to be careful not to test source code against itself. Ultimately, so I wonder if the derived model makes the analysis part any easier. I think so. I mean, at the end of the day, if you look at the formal methods from Daniel, they depict interaction between models, okay, between the different blocks, okay, and they cover all the possible states. Indeed, depending on your use case, depending on the hardware you are on, you would have different state transitions. So I have the feeling, yes. So we should be able to avoid this, you know, testing of the code against itself. Okay, I mean testing. I mean this risk. We could have this risk on the single blocks, right? And we need to be careful there. And this is why I said the tricky point here is the right granularity. But when we talk about interaction between blocks, I don't think we have such a risk, Johan.
Well, then let me rephrase my what I tried to express. Well, looking at this from the safety perspective, I have some requirement I need to be fulfilled by the code ultimately. Now we have a model that reflects the behavior of the code ultimately. And we can, if I understood this correctly, verify that the system actually behaves as the model describes it does. Mm-hmm. Now the step that is relevant now is to make sure that the model also fulfills the requirement posed to it from the safety side. And that's where I wonder if these models help.
Yeah, indeed it does, because I mean, if you look, yeah, go ahead.
I think that the main point of the discussion here is that the idea is to use the maintainers as a starting point and to try to use some sort of automatic interpretation of the code or some kind of reverse engineer to get a starting or an idea of how the system behaves. But the final goal is actually to model parts of the system based on the requirements that are imposed by the certification authorities, right? That maybe that's the thing that's creating confusion on the discussion.
And I completely agree here. The confusion is that the certification authorities will not formulate those requirements. They come from the system integration point of view. And now, who says that all this information presented in a different way is helping somebody else to derive that his safety requirement is fulfilled? I don't see it.
Lucas and Daniel, I think our time is up, and this is only an opening shot here. And I think we have a lot of good questions. We have a very, very good start here, but nobody is making claims that this has been closed. So, and as I wrote, you were invited to join future discussions, and I hope other people on this call have been interested enough to come and contribute, and on specific weekly calls of ELISA, which will be dedicated to this topic. Okay, I think our time is also up. Gabriel, unless you have something specific, I would just thank Daniel and Gabriel and leave people to think about this, digest it, and come up with even more questions for open discussion. Okay?
So Ilana, before you shut down, could you save the chat? Because there are lots of questions, like 40 messages.
Yeah.
Please do that.
Most of them have pretty much been covered. They're just more same, but definitely should be saved.
Yeah, just go ahead and save those if you can. Thank you.
It's an important contribution, and I think it should be saved. And okay. But thank you.
Okay. Thank you, guys. I see.